Okay, I'd like to welcome everybody to New Trends in Nanophotonics. Our first speaker is Professor Vladimir Shalaev from Purdue, and his title is Metamaterials at Crossroads, from Quantum to Space-Time Photonics. Vlad.
Okay, let me start with thanking Saeed and Ortwind for organizing this conference and inviting us. So this is a nice conference and a beautiful place. Okay, so I'll start with quantum photonics based on avalanche-enhanced single photon optical modulation and single photon emitters that we discovered in silicon nitride, which we think could be potentially very important. Then I proceed with negative index metamaterials, which historically were the driving force behind the whole field of metamaterials. And I end up with, to my perhaps biased opinion, most exciting things which going on in the field of not only metamaterials, but arguably optics in general. It's what we call space-time photonics. All right, I'll start with this quantum photonics, and as I mentioned, I will discuss this couple things. And I'll start with transistor. So we already discussed transistor quite a bit. And of course, there always was this idea to have an optical transistor, which potentially could act much faster. So, I mean, one of the ways to do it, very straightforward one, is to use this Kerr effect, the fact that refractive index depends on intensity of light. So then with a control beam, you would control properties of your probe beam. The problem is this, that this N2, which is Kerr effect, Chi3 effect, is extremely small. So to noticeably change refractive index, you have to apply really high intensities. So, and then my postdoc, Dimit, came up with this very nice idea, so I could not even believe that nobody thought of this. Apparently, for some reason, they didn't. So, and that's based on a very well-known device, which is called SPAD, single photon avalanche diode. So in this device, actually, with one photon, because you create avalanche of electrons, you get very strong response. And then it was a straightforward idea. Why don't we repurpose it for the to make optical modulator out of this? So the way it works, you have this single photon. It incident onto this p-n junction. You apply strong voltage. This electron brings this photon, when it's excited, brings electron from the valence to conduction bed. Then it's accelerated by voltage, create two electrons, and so on and so forth, and you have this avalanche. So the thing is that with one photon, you create up to 1 million electrons in a hole, in an extremely small area. And the process is very fast. It operates at the scale of picosecond. That's how much time it takes to develop this avalanche. So, and then it's quite obvious, okay, if with one photon I change so significantly optical properties, I could probe it by another beam, and that would be my optical modulator, optical switch. So, and if I do, that's the way it would operate. So we have first beam with a frequency above the band gap, and with one photon you create avalanche, and then you probe and change in refractive index. And the thing is, if I use this textbook formula, then I would immediately obtain that one single photon, I change refractive index by 0.1%. This is remarkably huge, one single photon. And if I put it in a cavity with relatively small Q, I could make it 100% easily. And it's fast, and most importantly, it's silicon-based. It's the most compatible. It's already existing. So in our first experiment, we just took conventional SPAD from a shelf. Of course, it could be dramatically improved, and that's what we're working now on. But in the very first experiment, what we obtained, so we had this control beam at 520 nanometers, and it was just a series of pulses, and there was less than one photon per pulse on average. And we would use this chopper, which basically modulate with certain frequency, close to kilohertz. And then we sent a probe at telecom and see at the detector when this probe is reflected from p-n junction, that same oscillation in the same frequency. Clearly, this control beam modulates the properties of my probe beam, and you're actually doing it with single photons. That's the very simple idea, and that happens because one photon creates up to 1 million electrons and holes because you create this avalanche. So I skip all these dynamics, which we measured already, but the bottom line is that there are two responses. One is relatively slow, it's around the microsecond scale. The amplitude is huge. If I would, this N2, this coefficient, it's higher than anything reported by orders of magnitude. So that's related to thermal conductivity and charge transport. And there is also faster response, nanosecond and sub-nanosecond, which is smaller, but still huge, much larger again than anything reported. If you look at the Boyd's textbook, you don't see this type of numbers there. And that's quite fast. So we could also make it out of the single photon detector, use optical detection that could improve jitter time and so on. That's what we are all working on. And most importantly, again, it's the most compatibility, and of course you could integrate with on chip. All right, so the other thing is this single photon emitters. I mean, the material platform of choice for photonics, nanophotonics, including quantum photonics, is silicon nitride. For the obvious reason, because if you, it has huge transparency window to begin with, relatively high refractive index, and most importantly, really huge these really small losses, which could go as small as 0.1 dB per meter, which is remarkably small. The problem with silicon nitride, people didn't have single photon sources if you would like to do quantum photonics rather than conventional classical photonics. And of course, you could bring these quantum dots, but that integration becomes complicated and you unavoidably would get lots of losses. And that's what we discovered, actually, this intrinsic single photon emitters, is silicon nitride. So there are two problems to solve. First one, it's well known that silicon nitride has strong fluorescent, autofluorescent background. You need to get rid of this because even if you have single photons, it's hard to see them when you have that strong background. It turns out that that could be accomplished by simply enriching silicon nitride with nitrogen. And then you see that this background just goes away. It works really remarkable, so no background anymore. Next step, how to create these single photon emitters. And for that, we just use this rapid thermal annealing. And what we believe is happening, although it's speculation at this stage, so because silicon nitride is sitting on silica substrate, when you do this rapid thermal annealing up to, let's say, 1100 Celsius within a few minutes, what happens, because of thermal expansion coefficients are different for these two materials, you create strain. And strain causes these atom-like defects. And as a result, you start seeing really bright emitters at room temperature. And the properties are quite remarkable. I mean, you have up to 10 billion counts per second. This is a par with best emitters reported ever. And so the purity, which is measured by this autocorrelation function, is also quite good. For room temperature, it's 0.1. It's quite impressive. It emits indivisible. Well, one could say it might be a problem. I would say it actually could be advantage. Why? Because it's much easier to do all this manipulation of photons in the visible, switching, rerouting, and only the final stage down converted to telecom and sent it to the fiber. So how to create them deterministically in any position I want? For that, we use this idea of making these pillars of silicon nitride, basically small cylinders. Why? Because when you do this rapid annealing, the strain you create depends on the diameter of these pillars. So, and by properly choosing this diameter, in our case, it turns out to be around 150 nanometers, which is easy to make, easily with photolithography, for example. So we actually obtained really remarkably high yield for first try. And we would pick up 55 columns in the arbitrary chosen row and obtain the yield at the level of 67%. And this is much higher than it would than you would obtain for the case when you do it randomly. Then it would be Poisson, it would be around 30%. So it's already more than twice higher. So by further optimizing, we hope to bring it to 100%. That work is in progress. So we also coupled successfully these emitters to waveguides, and we could use this inverse designed coupler. and place here this pillar, and it would couple to a waveguide, and at the other side we would detect this single photon and show that it is single photon by measuring G2. That's already been demonstrated. So we are in a position actually to create a bunch of these emitters coupled to waveguide and do circuitry. So let me address a problem which is quite generic, which is light matter coupling. And for the obvious reason, it is actually small, because the wavelength is so much bigger than the size of atom or qubit, orders of magnitude. Therefore, interaction is small. And the way to increase this coupling was proposed by a graduate of Purdue University, the same school where I have privilege to teach, Ed Purcell. In 1944, I believe, he published this paper, which was just one paragraph long, and basically the idea was trivial. If you have your atom, or whatever it is, dipole, which couples to light, and if you put it in a cavity, then because light bounces between mirrors many times, you effectively increase the coupling. And this increase would be proportional to the quality factor Q, quite obvious, and inversely proportional to the volume where your electromagnetic mode is localized. The latter fact actually enables Plasmonics approach, because rather than going for high Q, which normally is accomplished with dielectric cavities, where it could be up to 100 million, you could go to extremely small strong confinement. With Plasmonics using gap plasmons, you actually could confine electromagnetic mode down to 5 nanometers. And since it goes like lambda cube volume, so 5 nanometers 100 times smaller than the wavelength, so you raise it to the power of 3, you get million, just because of the confinement. So there's two approaches, and of course Plasmonics is much faster, because Q is not that high, like 100. Basically, you're talking about terahertz band and a picosecond speed. So there's two complementary approaches, and both of them have certain advantages and disadvantages, but that's the way to increase light matter coupling. What we recently did, we used this inverse design topologically optimized cavities that Alexandra mentioned today in her plenary talk. This is actually truly amazing, and the idea comes back to Ole Zygmunt, Technical University of Denmark. But it turns out that with dielectric, you could have really high Q, which is not surprising, in this case, easily 10 to the 4. But what is surprising, you actually could confine light down to the size much smaller than the wavelengths. So I would say it's not that trivial to understand, but I would say my simple intuition into this, by having all this decoration near this bow tie type of structure where the actual energy is localized, you kind of switch on destructive interference, and you cancel field all around this area. As a result, it really concentrating in extremely small areas. So by fabricating these cavities in silicon nitride, we obtained truly beautiful emitters, around 700 nanometers. And there was a recent paper from India, theoretical paper, when they predict that there are actually 2 zero phonon lines, and one of them is actually around 700. Although we're not 100% sure, we are doing right now this low temperature measurement, it's quite possible that this is zero phonon line, but this is really beautiful. I mean, it's sharp, beautiful peak, and actually we don't know even the width, spectral width, because it's smaller than the resolution of our spectrometer now. G2 is quite good, and the next step we are doing, at top of this topology optimized dielectric cavity in silicon nitride, we now place this plasmonic antenna, gold antenna, to make this hybrid structure. So we kind of trying to take all possibilities to control light matter coupling here. So the vision here is to having these single photon emitters, couple them to waveguide, have all this circuitry. If needed, we need to speed up the rate with which is single photon emitters emitted by using these plasmonic type antennas or dielectric or hybrid cavities, with the goal that to make this rate of emission higher than the rate of decoherence. And if that happens, then my photons would be indistinguishable. And that's really important for a number of applications. Speaking of plasmonics, since it's kind of the field I started my research activity a long time ago, normally, this dramatically enhanced optical phenomena, which Jeremy Bamberg was talking this morning, were first observed in random composites, which tend to have quite non-trivial morphology. They're actually self-similar, or mathematically you say they have fractal morphology. What it means that if you have this, let's say for example this fern, you could see that the structure of the whole is repeated on a progressively smaller scale. So that's what fractal is about. It's scale invariant. So if you have an aggregate of colloidal particles, like in this case silver particles, it's still self-similar but statistically on average. What we showed in early work was done with Mark Stockman, we showed actually that even though you excite this plasmal excitation in single particles, and of course they couple, and you would expect that normal modes are formed, and normally they delocalize, like phonons, polaritons, whatever, they actually, because of the fractal morphology, they tend to be localized in extremely small areas, which we refer to as hotspot. And since that actually, like people call it hotspots. And in these areas, the local field exceeds the field in the incident light by orders of magnitude. And that's the nature of this dramatic enhancement people observe on random surfaces, which are self-affine, or this colloidal aggregate, or many other structures. Nonlinear surface-enhanced Raman scattering, that's all eventually related to these hotspots. Well, one more thing to mention here. The properties of this material depend not that much on material it's built of, like silver, but rather on geometry. I pointed out that in this case, fractal morphology enabled this strong localization in hotspots. And that's very much similar to metamaterials, because the whole idea behind metamaterials is to design your optical properties, but it will. In this case, it's done by Mother Nature, whereas with metamaterials, we do it at our will. In the very beginning, the field of metamaterials was driven by the idea of negative refractive index, which is truly fascinating if you think of this. But it's not new, actually. As long ago as like in 1904, Sir Arthur Schuster, who was German, living in the UK, wrote a book with this modest, humble title, Introduction to Optics, and clearly indicate that refractive index could be negative. It doesn't contradict any laws of physics. So Mandelstam, in his lectures in the 40s at Moscow State University, also would discuss negative refractive index. But the one who actually made a difference and, of course, introduced quite a number of, let's say, movement in the field was Victor Wieselhager. In 1968 paper, he pointed out the way to make this refractive index negative. He would say for that you need both dielectric permittivity epsilon and magnetic permeability being negative. Then he spent decades trying to find these materials in the nature. He was a close friend, visited many times Purdue, but didn't succeed. And of course, then people started to engineer these structures. And in modern era, of course, Sir John Pendry did a lot of remarkable job suggesting things like perfect lens, electromagnetic cloaking, transformation optics, you name it. So that's what happens in a material where you have negative refractive index. Not only it goes in a different direction, which is not surprising, it's not a big deal. What is surprising, that the phase starts counter-propagate to the Poynting vector. That is truly amazing, and I like to give this example. If you like throw a stone into water and ripples, instead of going outwards, go inward. Phase counter-propagating the flow of energy is quite surprising. And that's exactly the property which eventually enables super resolution, proposed by John Pendry, or let's say transformation optics, when one part of optical space, which depends on n, the Fermat principle, basically cancels out the other part of the space so that it looks like light doesn't propagate. So that's a pretty amazing thing. And when it comes down to the history, so as I pointed out, Wieselhager suggested how to make it. Sir John Pendry was first to show the recipe how to make this negative n in the microwave range by suggesting how to make epsilon and mu. And David Smith was the one to realize it in this 2000 year and 2001, and he first demonstrated in microwave negative refractive index. And our group demonstrated the first optical materials with negative refractive index. It happened in 2005. So this is David's structure. Basically, it consists of this diluted metal to enable epsilon at low frequencies, because you need smaller plasma frequency. In this case, you have these wires, which acts like diluted metal. And it has these split-ink resonators, which enable negative mu. Together, you get negative n. And this is our structure using pair of rods. And it turns out together they could enable both negative epsilon and mu. And that's the structure where we first demonstrated negative index at telecom, 1.5 micron. In the same structure, 5 years later, when we replaced dielectric between these rods with active material, in our case it was dye pumped with light, we actually demonstrated first loss-free negative index metamaterial, which basically was gain compensated. Loss was compensated with gain. Well, with conventional metamaterials, we control light in space domain. We recently developed this time variant media. You have this opportunity to control in time domain. Altogether, you could enable this four-dimensional space-time photonics. So, but to make it possible, you really need this material where coupling to light is dramatically enhanced and has this type of kind of singular behavior. And that's so-called epsilon near zero materials. So what happens in this case, because epsilon goes to zero, the phase velocity diverges. It means that light propagates with no retardation. So that's quite remarkable if you think. And the wavelength diverges, which means you have microscopic coherence. Again, you basically have optically oscillating frequency, but especially it's like quasi-static, because everything wavelength diverges and there is no phase retardation, ideally, of course. And yet another thing is group velocity goes to zero, if you could see, as you could see from this formula. Why it's important? Because as Steve Harris pointed out long ago, if group velocity goes to zero, the light-matter coupling increases dramatically, simply because light has more time to couple two atoms. So that's exactly what happens in this case too. And finally, you have this boundary condition, which tells us the normal component of displacement current, displacement vector, has to be continuous, which means if in one of the materials epsilon goes to zero, electrical field diverges. Yeah, field enhancement. So that gives you a flavor that we're dealing kind of extreme optics, very unusual one. And luckily, there is this class of materials that Sasha mentioned in her plenary talk, transparent conducting oxides. They're transparent, so losses are not that high, and they have this ENZ in the important range of telecom. You could see here epsilon prime crosses zero around telecom, and I could control this point by simply changing the concentration of the telecomponent. And the imaginary part is orders of magnitude smaller than in silver or gold. So they kind of sweet spot. They're not as highly concentrated by charges as metals, but higher than semiconductors. They just do the job for what we need. So another important thing, of course, since we are talking about free electrons, they're described by this Drude formula with plasma frequency given by this well-known formula, which means if I use intraband excitation, then I increase the charge carrier density, my plasma frequency moves to the blue. If I now do intraband excitations, because of non-parabolicity, the effective mass increases, which means that plasma frequency moves to the red. So I could switch it to the blue, to the red, and the beauty of this, I could do it extremely fast, on femtosecond scale. That's the beauty of this transparent conducting oxides. And of course, it has been demonstrated that these materials have remarkable nonlinear properties. I believe the very first paper was done by Purdue group, when Marcella Ferreira was with us at the time, and we published in 2015, where we showed this dramatically increased switching, like 100% in these TCOs. Then we published this series of parallel papers looking at various nonlinear phenomena enhanced by NZ regime, and Bob Boyd did kind of in parallel and independently similar type of observations. So we obtained the enhanced Kerr effect, four-wave mixing, optical phase conjugation, you name it. Orders of magnitude enhanced, really dramatically enhanced. So let's look now what happens when light goes through the temporal interface. Normally, when you have a spatial interface, Frequency, of course, is conserved because the energy of photon should be conserved, but the momentum is not, and that gives us Snell's law. If I now abruptly change refractive index in time domain, because of space-time duality of Maxwell's equations, you could expect right away that in this case, momentum should be conserved, but frequency is not. You have actually something like Doppler shift. And that's actually this, what we call time refraction. And it was first demonstrated in our report in Clio in 2016, where we showed that when you abruptly change your dielectric permittivity by sending a pump pulse, because momentum should be conserved, you have to have the shift in frequency. And that's what happens. You change the refractive index, K should be conserved. As a result, frequency shifts, and that's what we observed. And the most remarkable thing happened if you do it periodically. So I'm actually honored to give this a talk chaired by the father of these photonic crystals, which is an absolutely beautiful idea. But if you ask me what particularly important about these crystals, is the possibility to control light matter coupling. Because if you have modulation in space domain with the period matching the wavelengths, and if you change your refractive index on the order of 100%, then you have this refraction and reflection, and because of interference, you have these band gaps formation for photons. And you have these forbidden bands. You have these gaps where actually density of photonic states is 0, so that's the way to control light matter coupling. However, because frequencies, energy of photon is conserved, and you cannot have propagating solutions in the band gap, they cannot be sine or cosine, but they also cannot be exponentially increasing. The only way is to be exponentially decreasing, evanescent waves, and that's what happens. Now, let's say if I do the same thing, but in time domain, I periodically modulate properties in time domain. Again, because of space-time duality, I expect the existence of the formation of band gaps in K-space. But in K-space, frequency is not conserved. Therefore, I can have exponentially increasing solution. And that's actually what predicted. So it means that photoluminescence could be exponentially increasing. You could get entirely different lasing regime. It becomes really interesting. But can you modulate with such a frequency? That's a big question. So this is an experiment we did with Modi Segev in Technion, which kind of gave us hope. Because what we showed, we would send the pump at 800 nanometers with progressively shorter pulse duration, going to 6 femtosecond. And for probe at 1225, if I recalculate it, it's roughly 1 cycle. So, and because momentum should be conserved, if pump changes refractive index, the frequency shifts, as I pointed out. And you could see this rise and drop in frequency shift, which is related to decrease and increase refractive index. When the refractive index increases, frequency moves to the red. When it decreases, it moves to the blue. But the thing which we obtain, it actually becomes comparable to the light cycle. So it's actually faster even than the typical electron phonon relaxation. That's quite amazing. And I should say, we still don't have a theory what exactly happened there, but there are some, let's say, some progress, and that's what I'm about to show. One of them related to what Sasha mentioned today. There is one thing which happens extremely fast, and this is electron-electron relaxation. It happens on the scale of 10 femtosecond, comparable to the scale we are considering. So in this case, you could use this two-temperature model, and you could actually see that at high intensities we are working at, the temperature increases, electron temperature. I will talk about electron. It increases truly dramatically. It becomes comparable to the Fermi temperature. So, and because of this quite interesting behavior, then when you do this intraband excitations, because when you do the pumping, the plasma frequency moves to the red. So whereas gamma increases, means that the imaginary part of the electric permittivity goes up, whereas the real part goes down because plasma frequency decreases. So they go in opposite direction. As a result, you have these oscillations. And that shortens the scale on which temperature changes. If you do interband excitations, in this case, charge carrier density increases, but effective mass also increases, which drives plasma frequency into opposite directions. And as a result, you have this oscillation in the refractive index. And again, at high enough intensity, you actually have extremely short responses that could be comparable to the light cycle. So by using this idea and this just simulation, we actually were able to fit the experimental observation by Mori Segev's group, which we did in collaboration a few years ago. So first, what you have, plasma frequency decreases, because we are talking about intra-band excitation. Effective mass increases, plasma frequency decreases. As a result, transmission goes up. Then Drude damping starts to increase, and that results in the fact that transmission becomes smaller, and at higher times, actually, Drude damping decreases, which results in the rise of transmission again. I'm not in a position to say that's exactly what's happening there, because there could be also coherent light-driven response when the electron simply follows the field. But in my opinion, at least this does contribute. But the interesting questions keep arising. When we looked at the change in refractive index as a function of intensity, we observe quite remarkable thing. So this is at 3 terawatt per square centimeters. We are talking about extreme optics here, like 6 femtosecond and huge intensities. So when I increase it to 5 terawatt, the change in the reflection becomes larger. But when I change it to terawatt, to 10, it actually completely changes the sign, which means that you kind of switch from one nonlinear response to another one. And that actually was first obtained by Mori Segev's group. They reported it last year, but it remained unexplained. And I believe we now came up with the explanation of that. So what we believe is happening, first you have this intra-band excitations. But this is, the conduction band is actually filled with electrons. You have this Pauli blockade. But when you do this intra-band excitation, you actually lift up Pauli blocking. You create these holes, and as a result, you have the opportunity for 2-photon excitation from the valence to conduction band. And that's actually confirmed by this quadratic dependence, which we observed. So basically what will happen, you first lift up this Pauli blocking, and then you have 2-photon absorption, which actually blue shifts the plasma frequency, which is opposite to red shift when you have the intra-band excitation. And that's what changes the sign. So we use simple rate type of equations, balance equation, considering all these valence, conduction, the electrons at the bottom and the up, and it fits actually remarkably well. So it looks like it is at least a good candidate to explain this phenomenon. All right, I guess I stop at this point, and I started with this quantum photonics, with a couple of things which I think are important. There's optical modulation at the level of single photons enabled by avalanche, and these single photon emitters, intrinsic one, which we now create in silicon nitride. And then we discuss how we moved from negative index metamaterials that inspired the whole field to this beautiful space-time metamaterials, where we have lots of questions and only started to get some answers. Thank you.
So let's have some questions.
So thanks a lot, Vladimir, for a nice talk. It was amazing. So I have a question regarding the single photon emission in silicon nitride. So I have seen that you are planning to couple the emitters to waveguides in plane. So I'm wondering about the direction of the emission, so the defect symmetry or whatever. So that is out of plane, in plane. How can you couple efficiently in plane?
So first of all, we optimize the coupling through this inverse design coupler. But in terms of how this dipole is rated off-plane or in-plane, we're still looking into this. And when we will learn this, we probably will increase the efficiency from 67% to 100%. So that's a very good question. We don't know yet answer to this. But what we believe it's happening in the center of these pillars. That's what X-ray shows. That's where a singular point is. The orientation is something to look into. Thanks for asking.
Thank you.
Vlad, for the last result that you showed, you had a model that included 2-photon, 3-photon absorption, right?
Yeah, 2 photons.
Yeah. Can you say something about the level, the value of the coefficients and how you fit them, how they match compared to other materials?
I mean, in terms of 2-photon absorption, it's just interband absorption. There are no any special resonance. It's not like high or whatever. Just keep in mind that we work at extreme intensities, and the advantage we take is ENZ regime. So like local fields enhanced and this type of things. But in terms of the cross-section themselves, I mean, this is just interband excitation. I don't expect any difference.
The magnitude, can you compare this to gallium arsenide or something like that?
I would say, I mean, bands are bands. I don't expect them to be too much different. The only thing I could say that in transparent conducting oxide, the reason why they're so fast, there are defects in the band gaps, which speed up actually the relaxation, we believe. And because of that, it could be actually increased. There are some states in the gap. So therefore, it could be actually faster than in semiconductors. But the magnitude, I would have to look it up.
You mentioned the intensity. So what was the intensity?
Terawatt, up to 10 terawatt per square.
No, 10 terawatts per square centimeter.
Right.
So it's 10 to the 13.
Yeah, that's right calculation.
Okay.
The work on negative epsilon is very interesting. But what happens to electromagnetic symmetry? Michael Berry calls it electromagnetic, almost politics, if you like. So why is there no work on negative mu rather than just simply negative epsilon?
Well, when you talk about the optical range, negative epsilon is much easier to have than negative mu. The challenge in the optical domain, because the coupling of magnetic field components to atoms is by alpha squared smaller than the coupling of electrons.